So if we apply the first law and second law of thermodynamics for the cycles that we talked about so far, we can have the heat engine cycles and the refrigeration cycle. And this slide is about the summary for the heat engine cycles we have learned. We have learned about 4 heat engine cycles: Otto cycle, diesel cycle, Brayton cycle, and Rankine cycle. So by looking at them, then we can actually see the ideal process cycle analysis for each cycle. But if you really look at this table, then we can see a lot of common processes for different cycles. So no matter what cycle we talk about, the cycle should have 4 processes. And when you talk about the ideal processes, each heat engine should have reversible compression and heat input, and reversible expansion and heat rejection. Okay, so these are 4 common processes that make the ideal cycles, no matter what cycles we specifically talk about. For an Otto cycle, there is a thermodynamic model of spark ignition engine, which can be modeled in terms of closed cycle analysis. And the working fluid is an air. And by working through all second law and first law for each process, then we can get those equations that you see for each process. Okay, same thing can be applied for diesel cycle, which is the thermodynamic model for diesel engine or compression ignition engine. So the diesel cycle is also considered to be a closed cycle, closed system analysis, and the working fluid is still the air. Okay. And we can see pretty close analysis results as we did for the Otto cycle, except the heat input process is different. Okay. Brayton cycle is a thermodynamic cycle for a gas turbine. Okay. The working fluid is the air. However, because all air should go through each component of the Brayton cycle, we should consider that each component of the Brayton cycle to be an open system. So with that being said, we can do the thermodynamic analysis for each process. Rankine cycle is a thermodynamic cycle of vapor power generation system. Because we use, in the case of water, as the working fluid, okay, and we have to use a lot of tables that you can find from the backside of the textbook. Still, the Rankine cycle should be considered to be an open system for each component. Okay? And each component can be analyzed by using the first law and second law of thermodynamics, as you see in this table as well. And that table is a really nice summary of how we can do this process analysis for each process and how we can get the performance analysis done. Like how can we calculate the compression work, how can we calculate the expansion work, and how can you calculate the net work, and also how can you calculate the efficiency. Even though you see only the ideal process results equations in this table, you should also know how to do the isentropic efficiency analysis when you have to think about irreversibilities during the compression expansion processes. Okay. Also, the air-based cycles, such as Otto, diesel, and Brayton cycles, are based on the constant specific heat case, as you see in this table. But you should be able to do the thermodynamic analysis when even the specific heats are not constant. So the question is that, can you really make use of the ideal gas table that is given at the end of your textbook to calculate those thermodynamic cycle analysis? Also, for the Brayton cycle and Rankine cycle, we talked about how we can add regeneration or reheating to boost up the performance of those cycles, such as in terms of power output and efficiency. So I really want you to understand how to improve those cycles. Then how about the vapor compression refrigeration cycle? So the basic concept of the refrigeration cycle is to inverse the heat engine cycles we just mentioned, we talked about in the past slide. So I'm not going to talk a lot of details about what you already discussed in the past lectures. But when you think about the refrigeration, the point should be paid onto the question about how much heat we can take out from a space that we really want it to be cooled. Okay? So if you look at this cycle schematic diagram, what you have to care is about the bottom, how much heat we can take out or we can remove, to make that cool. And in order to, make that cycle, we have to, input certain work to the cycle to run it, and we take a heat away from the space. Heat pump uses the same concept, but focus is more on how much heat we can, supply to the space we want to be warmed. Okay, so in that case, in this diagram, QH is more of your concern. And in order to do that, we have to input certain amount of work to the cycle. So in terms of gauging the efficiency of those refrigeration cycle, we define the COP, or coefficient of performance. And we defined this way, right? If you look at each process of the refrigeration cycle, we have to go through the compression and heat rejection and expansion, throttling expansion, and heat absorption. Okay, and we can, by applying the first law of thermodynamics for open system under the steady state condition, we can get those equations for each process to calculate the amount of work that we need to run the refrigeration cycle, and the amount of heat we reject from the cycle, and the amount of heat that we have to take in to the cycle. And by using these equations, we can calculate the COP for refrigeration and COP for the heat pump using the enthalpy differences for each process. And that is what we learned.